welcome to part 2. So there's a water molecule, and we can represent a water molecule like this. This guy here, we can represent it as a V. Okay. Now, magnesium will attract the oxygens towards it of water. Okay. Calcium will do the same. Like that. These are water molecules surrounding it. And barium will do the same. Okay. Now, interestingly, and this isn't definitely obvious, but which one do you think, crazy but true this, which one will attract most water molecules, the magnesium or the barium? Anyone? Anyone? Yeah, it's magnesium. Isn't that crazy? Lots of people would have said the barium because it's bigger and you can get more round barium. But in fact, it's magnesium. And now, why is it magnesium? Well, for the similar reason as we've seen before. All right. Now, as you go down group 2, the cation radius increases. And this leads to the charge density decreasing. Okay, so believe it or not, the delta H of hydration for magnesium ions is more exothermic. I'm going to say more exothermic. I'm going to say greater. Oh, that's not a water molecule anymore, by the way. That's a is greater than sign. Is more exothermic than the delta hydration energy of the calcium ion, which is more exothermic than the delta H hydration energy of the barium ion. Are we all okay with that? Are we good with that? So that's hydration. Now, obviously, all of these are exothermic. All of them. This one, they're all exothermic. So when I say greater, I mean, and this is a really weird thing to say, but I mean, what do I mean? I mean more, oh gosh, something's gone wrong with the matrix. I've got arrows on, I don't want any arrows. We mean more exothermic. So the magnesium is more exothermic than these ones. And this is the less, or the least, exothermic. Now, according to that, all of you understand that. That's good. Now, so that's one concept we've got to understand. Okay. The other concept we've got to understand. Oh, by the way, they're all sulfates. We're looking at sulfates. So if I hydrate one sulfate ion, it's exactly the same as hydrating another sulfate ion in calcium sulfate, and it's the same as hydrating a sulfate ion in barium sulfate. In other words, I can ignore the sulfate hydration because they're all the same. Okay, there's a sulfate, there's a sulfate, there's a sulfate. Now, the only difference with the sulfate ion is they will they'll hydrate with the feet first. If you look up here, it's the oxygen first, but if you hydrate these guys, it's feet first. But they're all going to be the same because they're all the same ion. So we can ignore them. Does that make sense? Are we good with that? Are we good with that? Yeah? Excellent. Right, well done. Now, there's another concept. Now, we are going to bring all this together, so hopefully you'll understand this. And this other concept is something called lattice energy. Lattice energy. Okay, now the lattice energy is this. Okay, it's God, what is it? I forgot what it is. Oh yeah, it's the ions. Let's have a look at a magnesium ion. There's a magnesium ion and a sulfate ion. These guys come together to form the lattice magnesium sulfate, magnesium sulfate, magnesium sulfate. Okay, now these ones are Mg2 plus, Mg2 plus, and Mg2 plus. These ones are SO42 minus, SO42 minus, SO42 minus. Now, when these gaseous ions come together, they form the solid. So up there we've got ions, down here we've got magnesium sulfate solid. Okay, and the equation for this would be this: Mg2 plus gas plus SO42 minus gas gives me MgSO4 solid. And that is, this is the delta H lattice energy for magnesium sulfate solid. Do we understand that, everyone? Excellent. Well done, Basadi. Thank you. Now, exactly the same thing happens for barium. Barium sulfate. Well, a small difference. The barium ions are bigger, so I should have done that bigger, shouldn't I? Let me use a different color. Color I haven't used before. This blue. We haven't used this before. Barium ions. Now, they're bigger. Okay, so let me draw barium ion and a small sulfate ion. The sulfate ion is the same as before. Barium ion, barium ion. Oh, they're pretty ugly, but there we go. Sulfate ion, sulfate ion. The sulfate ions are the same as these. They should be the same size. All right, so this is a barium ion, and this is a barium ion, and this is a barium ion, and the other guys are sulfate ions. Sulfate ion, sulfate ion, sulfate ion. Now, let's have a look at the hydration for this. Well, this is a similar equation. Barium, 2 plus gas, plus sulfate, 2 minus gas, gives me BaSO4 solid. Now, this will have a delta H lattice energy of barium sulfate solid. Now, what we're going to do now is we're going to compare these two things. We're going to compare the lattice energy here and the lattice energy here. So we've got the lattice energy of magnesium sulfate. And again, these are going to be exothermic. And this is going to be exothermic. But which one is more exothermic? Does anyone know? Lattice energy of barium sulfate. Which one's more exothermic? The magnesium? Yes, it's the magnesium. Well done, Laura. Now, in other words, this one, the magnesium sulfate, is greater. And what we mean by greater is more exothermic or more negative. I know greater and less than, we shouldn't use those terms. We should say more negative and less negative. I'm going to get to that, dear, don't worry. And this is less negative. Now, does anyone want to answer beside this question there? Why is magnesium sulfate more negative than the lattice energy of barium sulfate? Anyone? Anyone? It's a good question, Basadi. There's nothing wrong with the question. Anyone know? More Julius. Yes, very true, dear. That's what more negative means. Laurel, that is not an answer. That's just restating this. Okay, due to high charge density. Higher charge density, yeah. There's something that maybe you don't know, and I might spell this wrong. Fajans rules. Okay, you should look this up. You look this up on Wiki after we finish this lesson. Fajans rules. Okay, these are about lattice energy. Now, it's all to do with lattice energy, Fajans rules. Okay, and the lattice energy is bigger, and then when we say bigger, we mean more exothermic when, number one, the charge is greater. Okay, so that's definitely true. Yeah, it is a charge density thing, dear. Don't worry, we'll get to that. But the charge is greater. So, for example, the lattice energy of sodium chloride is going to be less than the lattice energy of magnesium oxide, because this is plus and minus, this is 2 plus and 2 minus. So the ions will be more strongly attracted to each other in magnesium oxide. Okay, that's a charge thing. And number two, Fajans rules, is the size of the ions. Okay, if the size of the ions is smaller. So let's have a look at this. Sodium chloride will have a greater lattice energy than potassium chloride. Okay, because when the ions are smaller, this is sodium, this is chlorine, this is potassium, and this is chlorine. The distance between the two, nucleus to nucleus, is greater here. Okay, the separation is greater, separation bigger. And if separation is bigger, the force of attraction, the attractive forces are less. Does that make sense? It is a charge density thing as well, Laurel. All right, are we good? So Basada, you're good. Excellent. So that's why lattice energy can change. Now, this is a complicated question you've asked me. Okay, so now let's have a look at the lattice energy, the hydration energy, and the heat of solution. Okay, so let's draw a lovely triangle here, and I'm going to dissolve magnesium sulfate, which is a solid. And if I dissolve magnesium sulfate, I get magnesium aqueous and I get sulfate aqueous. And this change, as you all know, is known as the heat of solution. Make sense? Okay. Now, up here, I can do my Mg2 plus gas, and I can do my SO4 minus gas, and I can put other arrows in now. I can put an arrow in here, and this arrow is the delta H lattice energy, okay? And this arrow is the delta H hydration energy, okay? Does that make sense? Does this, I don't know what you call it, Hess's triangle make sense? Yeah, there you go. So what we can say is the heat of solution, this one, is equal to the hydration energy minus the lattice energy. Does that make sense? Because from here to here, I've gone from that there to there, which is minus the lattice energy, and I've added the hydration energy. Okay, well done, Wanna. All right, now I hope I'm not boring you because this is quite a long. It's a lovely lesson, but it is quite confusing. All right, now, oh, thanks, Bethel, you're very sweet. Right, now, what am I going to do? I'm going to do my magnesium ions here, gas, plus my sulfate ions, gas. Okay, there's my ions. And down here, I'm going to draw magnesium sulfate, solid. Okay. Now, let's have a look at this. Going from here to here, okay, is the lattice energy. Okay. Going from here to here, is the hydration energy. But what is what is going from here to here called? Anyone? Delta H. Anyone fancy a go at that last one? Are we good? Besides that, something else. What's this last one? The one in green. Has everyone left? Maybe everyone's gone. What's the one in green called? The red one is lattice energy. Yeah, no, it's not formation, Laurel. It's solution. Well done, Wada. Because it's solid to Mg. I should have written these down, shouldn't I? Mg2 plus aqueous and sulfate aqueous. Okay, does that make sense? Sorry, Laurel. I should have written those in. Okay, so do you see that? Yeah, we're good there. So according to that diagram then, delta H is negative, isn't it? Delta H solution is negative. Solution is negative. Now let's draw the next one. Okay, now I'm going to draw these in the same line. The next one I think was calcium sulfate, calcium gas, and sulfate gas. Now what happens to the lattice energy? Well, because calcium is bigger than magnesium, the lattice energy is less. Yes? But, there you go, so there's the lattice energy. And this is calcium sulfate now. So this arrow for calcium sulfate is less than this arrow for magnesium sulfate. All right? Now what happens to the hydration energy? Well, ladies and gentlemen, the hydration energy is also smaller than the hydration energy for magnesium and sulfate. So they're both smaller, okay? So there is that. So what do I draw at the bottom here? This is calcium 2 plus and sulfate 2 plus. Now, there is my heat of solution, okay? This is delta H solution. And now, I'm sorry to, I hope I'm not boring you seriously. I'm going to do it for barium and sulfate. And now the hydration energy, the lattice energy is even smaller because as you go down the group, the lattice energy will become less and less because of Fasian's rules, because the ions are getting bigger and they're not as attracted to each other. But also the hydration energy gets smaller. Okay, so now, isn't this crazy? BaSO4, and now this is the hydration. And now, what happened to my heat of solution? Now it is endothermic. Okay, so what's the moral of the story? The moral of the story is for group 2s, okay, because the cationic radius or radii increase, okay, therefore the delta H lattice energy becomes more or less positive, less negative, I should say, sorry. Delta H becomes less negative, and delta H hydration becomes less negative as well. But which one changes quickest? But delta H hydration changes quicker. Does that make sense? Look, they're both decreasing. Lattice energy is decreasing. Hydration energy is decreasing. Well, the hydration energy is decreasing, Basadi, because of this idea. Do you remember, Basadi? No, yeah. The hydration energy decreases because the cationic size gets bigger. Okay, so the point is, for sulfates, the hydration, becoming more positive. What I shouldn't say gets bigger and gets smaller. I should say becomes more positive. You're quite right. Okay, but I think visualizing it is nice here. So I visualized it here. So what happens is, because the cationic radius increases, lattice energy becomes more positive and the hydration energy becomes more positive, but the hydration energy becomes more positive quicker, and therefore they're both getting more positive, but one's getting quicker than the other. And because of that, the delta H solution, as you can see, because of this, as you go down, delta H solution becomes more positive. And as delta H solution becomes more positive, the thing becomes less soluble. Okay, why does it decrease at a faster rate? Well, that's an interesting, but we'll get to that. But are you okay with that for now? Are we good with that for now? So basically, there's two factors. There's lattice energy and hydration energy. Okay. The way I think of it, by the way, is if your hydration energy is bigger than your lattice energy, the thing will dissolve because there's enough hydration energy to smash up the lattice. And as you can see from my diagram, in magnesium sulfate, that is the case. The hydration is bigger than the lattice energy. They both get smaller. The arrows get smaller from left to right. But have a look at the barium sulfate. Now the hydration energy is too small to break up the lattice, and therefore it will be insoluble. Does that make sense? Well done, Basadi. Well, I hope it does. All right, well done. It's a complicated topic, this, but it's beautiful. Okay, so Basadi there has asked this. All right, so for the sulfates, magnesium sulfate, barium sulfate, and what's the other one? Oh, these are enough, I guess. Now, as you go from this to this, they get less soluble. Okay, for the reasons I've given. Now, why does one decrease faster than the other? Well, believe it or not, because the sulfate ion, because this ion is a big ion, all right, lattice energy changes slowly. Okay. Oh, I know. I'll be very quickly there. I know it's over. Lattice energy changes slowly. So that it does decrease, but lattice energy changes slowly. Okay. Now, interestingly, for the hydroxides of the group 2, to calcium hydroxide, to barium hydroxide, the hydroxide ion, the OH minus ion, is small. Oh, okay, Rousseau. I thought you were here. She's gone to come back. So this ion, the OH minus ion, is small. Okay. Oh, go away, you stupid thing. So the OH minus ion is small. So for the hydroxides, because the anion is small, now delta H lat and delta H hydration energy both become more positive as before. But in this case, the lattice energy, in this case, changes quicker because it's a small ion, changes quicker than the hydration energy. In other words, they both become smaller, but in this case, the lattice energy gets smaller quicker, and that's why the hydroxides get more soluble going down. Hydroxides increase in solubility. Does that make sense? Going down group 2. Down group 2. Oh, guys, well done. I'm going to stop there because that's quite a lot to take in at once. Now, Musa, I'm